most of the theory part of the work I described was done at the Technical University in Munich, where I am in the group of Professor Billy Stern. So first I will give some reminder, which is hardly necessary but for this audience, but I will remind a bit why you want to study dissipation in these systems. Then I describe briefly the theory I've developed over some years to study this, and in particular the way this leads to a simple master formula for the Q values of the mechanical resonance due to the clamping loss that is very, very generic. And in particular, more recently, we have from this developed a generic Q solver with a group of Macroscopic in the context of studying some geometries that I described that is free resonator geometries. The idea of these geometries is that they not only provide a way of testing the theory in a very stringent way, but they also give a recipe for essentially getting rid of this problem of the clamping loss. And then I will go on to some other collaboration with experimentalists, this time in Cornell, with the groups of Pierre and Harold Kreitler, with whom we have studied this highly stressed silicon nitride resonators that are so popular. And basically this also provides a way of testing this theory. But the more interesting thing is that we also find here something that essentially is another path to getting rid of the clamping loss. And this one was not really known to the MEMS or MEMS community, so it's kind of interesting news for the experimentalists. So first of all, of course, and the main reason for trying to minimize the dissipation in the systems is because it limits a whole set of technological applications they may have. For example, they are very promising for signal processing devices, for example, on chip for high frequency narrowband filters. They also provide ultra-sensitive sensors that can be scaled all the way down to the molecular scale, so there is very interesting ideas for mass sensing, like weighting single molecules, also displacement sensing and force sensing. And in particular, something that's very interesting coming from quantum physics is essentially the idea of magnetic resonance force microscopy. This is essentially a form of high resolution scanning probe force microscopy in which you have a magnetic particle mounted on a cantilever, and the particle interacts via the magnetic dipole force with the nuclear or electron spins of the sample. And of course, the limits, the problem is that of course this cantilever also goes to a thermal back of the phonon modes, and in the end, this or other environments, and this ends up limiting the sensitivity with which you can do this thing. So this nice diagram here is taken from a very nice work from Vancouver, in which they managed to scale this idea, this concept down to the level of a single spin. So if you think of this, of going into the quantum regime of such a device, one could think of whether one could use maybe the cantilever as a measurement device to probe the quantum state of the spin. And so basically there is a connection between these more standard technological ideas and basically trying to understand the limits for displacement detection and sensing, and the idea of having this quantum limited control of a single macroscopic mechanical degree of freedom. So basically, if you're able to achieve this more sort of basic science goal, you know that you have all of these things under control, as Conrad pointed earlier in the workshop. And so basically, the first zeroth order goal in this direction is to initialize this oscillator with a long phonon lifetime in its quantum ground state. So one should qualify that one wants a long phonon lifetime because, of course, in nature you have many oscillators that are in the quantum ground state, but it is you would like to take this out of equilibrium to something interesting and have some finite time to do this. So this will be set by the mechanical, by the natural language of this mechanical resonator. And then one would like to go one step further, essentially, and demonstrate truly quantum signatures from the perspective of a theorist. This ground state is just a coherent state. So then one would like to have actually something non-classical in this state of motion. So there are ideas for Phonon jumps, for maybe not non-classical states, and of course, what people would like is to have this celebrated Schrödinger cascade, in which you have this superposition of two states of the mechanical resonator that correspond to different center of mass positions. So in a way, the recipe, I mean, in a way, what is one trying to do is essentially to take the ideas from quantum optics and apply them now to a mechanical degree of freedom. So what's been done in quantum optics is basically this realization of the James-Cummings model, in which you have a single spin 1/2 coupled to a harmonic oscillator. And now you would like to have this harmonic oscillator, instead of being a mode of the center of mass motion of an atom, or maybe an electromagnetic mode in a cavity, to have this the mechanical resonator, and then you need something for this equivalent of the two-level atom. So ideas that have been put forth and are way under being realized is this idea of coupling to superquadratic qubit. Then there are things that have been proposed but not yet quite realized, involving quantum loops, or maybe using an empty center, as I mentioned yesterday. So this would be quite nice. So in some sense, basically in the electromechanical domain, there has already been a demonstration of all this concept, which was done in the groups of Andrew Pierre and John Martinez. And this involved essentially this type of path where you have thickness oscillations. So the mechanical mode you're talking about is simply thickness oscillations. There is no overall center of mass motion. And this gives the piezoelectric effect couples to a phase cube. And what they were able to show were these single, essentially these vacuum Rabi oscillations, which you essentially oscillate between having one phonon in the mechanical resonator mode and having one excitation in the superconducting phase. But as it was pointed out yesterday, this thing was done at the expense of having a resonator that has a very poor Q. So the Q here is essentially in the hundreds. This essentially limits very much what you can do beyond this first type of demonstration. So something one would like to understand here is what this Q is. And then the other thing that essentially allows this to be realized is that here the frequency is very high. So it's on the order of 6 GHz. And these things go together. Typically, you would like high frequency and high Q, but these things are at odds. And people have loosely quantified this by using this frequency times Q product. And essentially, there are some mechanisms for which that is preserved, but in general, this is a bit of a loose statement, and it's not really the figure of merit for these more standard applications. And it turns out that if you think of the quantum applications, this emerges as an actual figure of merit from the main things you would like to do. So a simple example is, for example, this idea of cavity-assisted cyclone cooling, and in particular, maybe, I mean, this is not realistic at the moment, but maybe starting from room temperature and trying to go all the way to the ground state. And the way one can understand this is basically, imagine that I want to pull this mechanical resonation, so I bring in this ancilla system, there's a cavity, and I essentially choose the properties of my cavity and my laser fields so that I essentially optimize the minimal final occupancy I will have in this mechanical resonator. So if you optimize both with respect to laser parameters and the cavity properties like bandwidth, etc., what you end up is that the minimal occupancy you would have in the idealized situation for a given ambient temperature, a given Q of the mechanical resonator, and a given mechanical frequency scales like this quantity to the power of 2/3. So you see like here, essentially an FQ gives you a certain ambient temperature from which you can move to this low occupancy. So here this is a more precise statement, this idea. So basically, well, what we want to do here is essentially to try to predict what limits is mechanical dissipation, because you see if you can improve this by, say, factor of 10 or 100, immediately you're winning a lot. Similar figures of merit emerge for some of these other quantum ideas that have to do with comparing the coherence of the mechanical resonator with respect to the time scale at which you can do operations on it. So the relevant mechanisms at low temperature and high vacuum that are, so to speak, in a sense, kind of fundamental because it's alpha-induced getting rid of them in a solid state environment. On the one hand, people see that there is this environment of essentially effects or disorder that is dynamic and couples to your motion, and that can be modeled at low temperatures as two-level tunneling systems. So this is the idea of two-level fluctuators. This is certainly the one that has richer physics, and one would like to sort of understand this in the future, and people are only now beginning to take care of that for nanomechanics. Another thing is anharmonic effects, like phonon-phonon interactions. Typically, for the larger things, one would think is that if you lower the temperature, you get rid of all of this. In fact, there are many promising systems that is essentially like the idea of the ultimate size limit for this nanomechanics, that is, for example, the graphene drums or carbon nanotubes, in which these things will be only going away at ridiculously low temperature. So this is something else that one would also like to study here. And then there is the fact that even if you're at 0 temperature and everything is absolutely perfect, essentially your phonons will be ballistic then in the resonator, but you will still essentially couple to the supports. And so this is radiation of phonons into the supports. But this is of course a harmonic mechanism, so this looks the same also in the high temperature classical regime that it corresponds to elastic wave radiation. And so what I have focused is basically trying to understand this last mechanism and developing a comprehensive theory for that. So basically this question essentially boils down to asking the following, which is a fundamental limit set by the design of your resonator. So typically when people design photonic structures before starting, you try to see what the characteristics will be for that, and essentially you have a Q that you know that you cannot beat that comes just from solving the Macroscopic equation. So here we would like to do the same for mechanical resonators. Typically people nowadays do this for frequency, mass, and so forth. It would be nice to have the same for the Q. So one can say, of course, this is temperature and scaling dependent. There are caveats for that. I will not discuss too much. I just want to be careful when there is stress involved. But this scaling dependence is interesting. Basically, like, okay, we will see that the dependence on materials properties is not very strong. So it's mostly, and the dependence on geometry is much stronger. And so all of these applies equally well to small objects and to bigger objects. It's just that if you get too big, of course, you can have nicer, you can do tricks that you cannot do at the nanoscale. But for MEMS, this is equally applicable. So the point is, I talked about these different environments. In the case of the phonon-phonon interactions, typically these involve phonons that have frequencies that are different from the ones that are essentially resonant with your mechanical resonator. So the point is that in resonant regimes, all these things correspond to different environments, and essentially then the dampings will add incoherently. So basically the reciprocals of the Qs for the different dissipation mechanisms will add as 1/2. So this is important, and I'll come to this later in the talk. And it's important to have this in mind in terms of isolating each of these dissipation mechanisms. So the way that typically people have gone about discussing dissipation in the quantum regime, like quantum dissipation, is basically to write down what they call like a data-legged model, in which the relevant harmonic degree of freedom is coupled linearly to a thermal ensemble of harmonic oscillators. So this model is very nice because it can be solved exactly. And so basically you can integrate out the environment of harmonic oscillators, and you get essentially a generalized Langevin equation for your mechanical resonator mode. So basically, well, you have the inertia, of course, and the restoring force, and the two more interesting parts that come from integrating out the environment that are essentially a viscous force that opposes the velocity of the normal coordinate of the resonator. This in the general case in which you do it exactly will have a force and memory. And then there is the fluctuating Langevin force that will be related to this here, a fluctuation dissipation theorem if you have a thermal ensemble. So basically the point is that all of the interesting thing here is essentially determined by what is the spectrum of this environmental force that is exerted on the resonator. And so as you see, this environmental force spectral density boils down basically, roughly speaking, to the Fourier transform of this dissipation curve that sets the viscous force. And typically people use a linear model for this environment, and so then this dissipation kernel essentially becomes a delta function, so the memory here drops out. Then, of course, to have full Markovian dynamics, you also need the correlations of this to be quite. And in the more well-known context in which this has been used for mechanical resonators in the classical domain, people typically consider this linear thing in the limit of high temperature. So then you can show that the full thing is fully Markovian. And it's important here to note something, that now in the task that we have ahead, that is this idea of the quantum nanomechanics, the situation is a bit different. There you're in a weak coupling situation in which you want this ultra high Q. So basically the situation is much more similar to quantum optics, where this Markovian dynamics is emerging for a different reason. This is weak coupling approximation. And with the weak coupling approximation, basically it doesn't matter whether it's linear or not linear, but you want is simply to pick up the value of this at the resonance frequency. But what matters is, of course, that this should be significant. But then if you think of interesting things that you will do with a resonator, like essentially preparing this crazy states and so forth, typically you need to couple the resonator to something else. And that's where this Markov approximation may not be enough if you want to go into more detail in this quantum nanomechanics. So this is something more for the future. An example would be, for example, this thing I showed with the cantilever and the spin. You could have this kind of structured spin also model at low temperature, in which you have some defacing of the qubit induced by this coupling to the resonances. And for that you may want to know the full spectrum of this model. So it turns out there is something very interesting, that this mechanism that is essentially for practical reasons one wants to study first is also something in which you can essentially find out this spectrum from the microscopic physics. So basically this is what I've studied here. There was some seminal work first by Gross and Lifshitz on these things for the Q values. And so what I've done here is, well, not only develop this further to have this general understanding of what is the limit imposed on Q by the design of a small mechanical resonator, but also have this derivation of the full spectrum. So basically you have a microscopic derivation of this Caldera-Leggett type model in a case where you have a macroscopic mechanical degree. So this is sort of interesting from a theory perspective. The only other instance in which this can be done is for the electromagnetic field. But here you're talking about this collective degree of freedom of a solid-state system. So this can be found in this long Derby paper. And now I will briefly tell you a bit in a nutshell the idea here, because this is these data developments are basically based on this. So the reason why you have this high Q resonance is basically because from the perspective of elastic wave radiation, in the first place, these structures behave essentially like phonon cavities. So it's basically like a mechanical peripheral that you have. So to fix ideas, if we think of a beam structure, this could be either a cantilever or a bridge with a certain length and transverse dimension E. And the idea is that here at the support, you have a very bad impedance match to the transmission of waves. And so essentially this abrupt junction at the support works a bit like a mirror. And so basically you have your elastic waves bouncing back and forth, and this will generate essentially something like a Fabry-Perron. So if you think in terms of this low temperature thing, I mean this is a bit an idealist way, but it's sort of a neat way of thinking. At some point the mean free path of the phonon becomes longer than the size of the structure. And so then essentially you will have ballistic transport of the phonons here, and this will essentially have some probability of getting transmitted at this junction. So this is this idea of looking at this in terms of phonon-tunnels. Of course, the problem you have is harmonic, so it looks the same in the quantum as in the classical version. This doesn't depend on h bar, but this is a way of making more intuitive the kind of math that you use for solving this in an efficient way. And I will describe that in a moment. But okay, the first step here is, of course, to do this from sort of scratch. You need to have an elastic. You don't need to start from the lattice Hamiltonian because you are in a long wavelength situation compared with lattice spacing, and so essentially you can use elasticity theory. And so what you need is to develop the scattering modes of the whole structure. So the elasticity theory of the support coupled to the structure. The reason why this can be done, I mean, of course, from a scattering perspective, so you will have some waves that come from this indefinite support that is like a continuum of phonon modes. Some will be reflected, some will be transmitted, it will bounce back and forth. And the reason you can do this is because you have a natural small parameter that in the case of a beam is basically the reciprocal of the aspect ratio. So then you can do essentially a controlled expansion of all the different parts that you need here in your derivation in terms of this small parameter. And then there is another thing that you need to use, of course, this is this perspective where you look at the whole structure together. So it's this like modes of the universe. Then what you want is to extract the spectral density that describes the noise that is seen when you look at a particular resonance coupled to the state. So you need to go between two representations for the problem, like a closed system and an open system representation. And from this you can essentially reduce this spectral density I showed earlier to overlaps between these scattering modes, and a certain mode that is localized in the resonator, that is this resonator mode that will satisfy certain types of boundary conditions. For the beam, this ends up being quite neat because you get some general expressions for the spectral density, and you can look at that, you can express them either in terms of the support density of states or in terms of the transmission at this beam support junction. And these are like two alternative ways that can give you some intuitive understanding of the results. The transmission one, of course, ties to this phonon-tunneling picture. So what you get for this beam geometries, for example, basically you have four low-frequency phonon branches that have no infrared cutoff, and so you have essentially four types of resonances that you can have in a beam. So you have stretching modes, twisting modes, and of course the bending modes. And as you see, then you can essentially derive one of these models for each of these resonances. They're indexed by the harmonic index K. What you see is that for stretching and the bending thing, you get this ohmic behavior. And this can be understood in terms of the density of states. You have the density of states of the support is omega squared, and this will, you will then be sensitive to the displacement of the support, so you pick another 1 over omega from the square of the 0-point motion of these things, and then you will get your linear behavior. And then for torsion, you see you have superomic behavior. And the reason is that you essentially couple to the angle at this support. So you are essentially taking a derivative of this continuum field to which you couple, and this gives you an extra factor of omega squared. Then this, I will not enter into the complexity here, but the point here is that this thing can be expressed in terms of parameters for this effective 1D theory for the beam. And so it's not really a property of a macroscopic beam. This can be applied equally well to an nanotube, for example. And gives things that are relevant in the case, for example, of stress. If you now think that everything is done of the same materials, what you get is this type of geometric scalings, but it turns out that the dependence on materials properties for reasonable materials is it's not a big thing compared with this. So you can, it's not really a geometric property, but it's mostly geometric. And so you see, for example, the more popular flexural modes, they go like the 5th power of the aspect ratio. So this explains why if you have these flexural things, you know, like if you have something big, this is negligible. But then if you have aspect ratios of say 20 for a bridge, you already have something that is comparable to what people have measured. Then you can have other situations, for example, consider that the supports are 2D, you have dimensions that are large, and then you get some kind of more peculiar behavior for the spectral densities. You can also consider a more realistic model for the bridge, and this is important. In principle, there will be some structure, and you will not get this power loss, you will get some interference effects between the two ends of the bridge, and there will be some modification of the dependencies there. So then, sorry? What do you mean by example, you have a pillar and you highlight this and you can excite this type of expression of the So those have those don't have Qs that are not so great, like the there are not, I mean, there are no high Q structures really like that, but there are some interesting structures from Mavalvala values. So, just surprising that this works. Yeah, these are matched so that everything is compared at the same frequency. And okay, and something one would say, the torsional modes are essentially immune to this pattern. So this has not been used so much, but in principle the numbers you get from this thing are much bigger for same frequency. The idea here is that you want something with a certain frequency and then you pick just the fundamental resonance and what would be the Q that comes out. So basically all of these things can be put in a more general form in terms of this overlap that can be expressed as a contact integral. So here S now is essentially the contact area between the mode, the resonator mode volume, and the supports. This Q labels essentially the scattering modes of the whole structure. The sigma is the stress tensor, and the U is the elastic displacement, and R, of course, is for the mechanics, for the resonator mode, and then the Q for the scattering modes. And so you can essentially have this type of expression where the spectral density comes out as this integral over the contact. And then if you look at this, essentially, it ends up giving this general formula for the 1 over Q. The idea is here, I mean, the first way you can look at this in terms of what I just described is essentially like a small contact approximation. So if you do that, basically, you end up finding out that the scattering modes can be evaluated to 0th order, and in some cases so that they reduce to the free modes of the support as if you essentially remove the resonator. This sounds like a trivial statement, but it's not so trivial in terms of matching that. But then one can essentially see that this is valid for an isolated resonance, provided that essentially this K here is a reciprocal of the length scale over which the resonator mode varies appreciably. This times D, it should be much smaller than 1. So this generalizes a bit this idea of large aspect ratio. So then the point is, what do you use for the resonator mode? And this is sort of intuitive. What you have to do is to collapse the contact. And basically, if you have a non-singular situation, like for example these toroidal structures that you have a pedestal, the thing will become free. So you will have a free boundary condition for the resonator. If you go to these beam structures, then of course you will have some cramped boundary conditions. And the support modes will satisfy the converse. And there is a whole mathematical theory that uses this type of sort of compatible boundary conditions. So this can also be understood in a more formal way. And then you find that this is valid for all sorts of things. So you can have pedestal geometries in which the contact is sort of essentially parallel to the substrate. You could have these planar geometries that are more common, in which essentially the contact is perpendicular. But the point that is very interesting is that there is now once that you know the answer, there is a sort of simple way of seeing how you would derive this. I mean, of course, there is a formal step then that gets complicated, but this is a very intuitive understanding, at least if you think of it quantum mechanically. So if you have the clamp boundary condition, you can think that essentially you write something in which you have essentially the